Okay, so we are going to talk about molar dilution first. So what is a molar dilution? Well, in science, a lot of times when we order chemical, we order it as a stock solution. And so we're going to use this equation right here, and we're going to dilute that down. And so the other two equations here are if you would happen to have to create your own solution, or if you are going to try to recreate a solution that was already made. And so we'll use those a little bit later. But let's start with our molar dilution. So with our dilution, again, we're going to be using the equation M1 times V1 is equal to M2 times V2. So let's see what they start us with here. So we have a 3 molar of Ki, or potassium iodine solution, and it wants us to make 0.3 liters, which would be our volume 2, of a 1.25 molar Ki solution. Remember, this whole year, we have been using molarities, or a molar solution. We just didn't know how to create them. And so this is one way that we're able to create a stock solution and then dilute down from there. So what we do is we start with our 3 molars of Ki over here. We're going to look for how much of that we need. So that would be our volume 1. We set that equal to what they want us to find. We need to make 3.3 liters, and we need to have 1.25 molar of Ki for that solution. And so this is a pretty easy one. We would have volume of 0.125 liters of 3 molar Ki is needed, or that would be 125 milliliters. You would add that to 0.175 liters, or 175 milliliters of water. And that would create your dilution for that. And that's what we actually do within laboratory. Let's try another one. In this case, it's giving us our stock solution, which will be our M1, of a 5 molar sulfuric acid solution. And it wants us to prepare, so that'd be our volume 2, 100 milliliters of that at 0.25 concentration. So a much weaker concentration of that, which would be usable for students. That's what I would probably give you. So here we go. We start with our 5 molar sulfuric acid. By the way, when you're dealing with a strong solution like this, you probably want to be in a ventilated hood. You don't want to just be hanging out at a lab station diluting this out. It'll burn your esophagus and respiratory system. We are going to dilute it down to a usable sulfuric acid. And so, again, we're just solving for that volume. We're already in milliliters, so we can stay in milliliters. It's not going to be a huge difference, but you're going to notice that we only need 5 milliliters of solution. And we should put 5 molar H2SO4. And we will add that to 95 milliliters of H2O. That should be a 9. So one thing that's special about this, we cannot add the 95 milliliters to the sulfuric acid. We always add acid to water, and the water should be sitting within an ice bath, surrounded by an ice bath. That is for safety purposes because it creates an exothermic reaction. It gets really, really hot. Okay, so now we're going to do molality. For molality, it's a little bit different. So we're going to have to find moles divided by kilograms. That's molality. So what do they give us? They give us our sodium sulfate, and it says it's in 100 grams or 1,000 grams of water. This should be your solution. This should be your solvent. This is our solvent. That is our solution. So let's make those conversions right away. This one's really easy because we know that that's equal to 1 kilogram of H2O. So that's an easy one. But now we have to take our 10 grams of Na2SO4, sodium sulfate, and convert that into moles of sodium sulfate. So we need to find the molar mass using the periodic table, and you get 142 grams of Na2SO4. And in this case, you would get 0.0704 moles of Na2SO4. All right, so now let's figure out our molality for this solution. So remember, molality is the ratio of the number of moles of solute dissolved in 1 kilogram of solvent. And it always has a lowercase m when we write this label. It's not molarity, it's molality. So we just want to take that. That should be a really easy conversion for us because we're dividing it by 1 kilogram. So then we have a molality of 0.0704 little m H2SO4. So that is our molality for that. Let's do one more molality problem here. So it says we have a molality of a solution of 30 grams C10H8. And again, we want to convert that right away into moles of C10H8. And that would be 120 grams if we look at our 28 grams if we look at our periodic table. And in this case, you would get 0.234 moles of C10H8. So now toluene is our substance. Now before it was water. Water is our universal solvent. Doesn't matter if we're in toluene or if we're in something else. No. This is an easy conversion as well. It's a 0.5 kilogram. So we want to set that over. I apologize. My pen is like delayed. So then I feel like I have to write it again and it's not quite working. And so then what we get for this is a 0.468 molality of our solution of C10H8. And remember, this is going to, the solution containing 1 mole of a solvent per kilogram of solvent is a molar solution. So now let's look at molar fraction. A molar fraction is a ratio of the number of moles of a solute in a solution to the total number of moles of solute and solvent. So this becomes useful if we have an unknown solution. We have to try to figure it out. So here where it said, what is the molar fraction for just Na? If we have an aqueous solution of 22.8 grams per mass. So one thing that we should remember is we've already done the equation for percent by mass. That was our section 1 stuff. So percent by mass, again, is equal to the mass of our solute divided by the mass of solution times 100. So we have to remember that first. So if we look at that, we're going to just assume this. Just like we assumed when we were doing our formulas for empirical formula and molecular formula, we don't have any other numbers. So we're going to assume that this is out of 100% because that's usually what they are. And this number is 22.8 grams of NaOH. So this is a molar fraction. The key word here is mole. So we have to convert grams to moles. That would be our first step. So we know that the molar mass of sodium hydroxide is 40 over 1 mole of NaOH would give us the number of moles for this to be 0.57 moles of NaOH. Now, I'm not going to arrow back up to the top, but you should know that, hey, for a molar fraction, you have to have the moles of both the solute and solvent. Well, we only have the solute. So how do we figure out the solvent? Well, what is the universal? Oh, yep, you guys got it. It's water. So when we take this, we know that this percent by mass is of the solution. So if we have 22.8 That's going to be this. Then we subtract that from 100, and an absolute value would get you 72 or 77.2 grams. That 77.2 grams is of water, because water is our universal solvent. So then we divide that by 18 to get our moles, and we would find out that we have 4.29 moles of H2O. Now that we have both of those, we want to find our X for our solute, because that's our sodium hydroxide. So that's going to be our molar ratio. We don't have to find it for both. We just have to find it for this one. So we just want to take our 0.57 moles of NaOH divided by 0.57 moles of NaOH plus 4.29 moles of water to get 0.117. We do not have a label for a molar solution. That is just for our solute. So we just leave our answer like that. So let's try one more that's a little bit tougher. In this one, you'll notice that it gives us the molar fraction for sodium chloride. And it says it's dissolved in 100 milliliters of solution. Okay, so we do know a couple things. Sodium chloride dissolves in water, so our solution is probably going to be water. So we want to take our 100 milliliters. We know that 100 milliliters of H2O has a mass of 100 grams of H2O, because we know 1 milliliter of water is equal to 1 gram of water, because the density of water is 1 gram per liter. So we're going to convert this now into moles. So we can convert that into moles. So you take your 100 divided by your molar mass of 18, and you get 5.56 moles of H2O. Okay, so now you're thinking, well, great, that doesn't really help me out a whole lot. So I'm going to kind of arrow down just a little bit and show you something, and it's the reason how I'm going to get the formula. So here's what we know. 2.1 is the molar fraction that was given to us for our solute. So we know that moles of NaCl is going to be equal to moles of NaCl plus moles of H2O. We know that. We could work this out to get 0.21 moles of NaCl plus 0.21 moles of H2O, and set that equal to moles of NaCl. We also know what the other molar fraction is, because we can subtract that from 1 to get 7.9, and that is equal to moles of H2O over moles of NaCl plus moles of H2O. Apologize for my penmanship, it's atrocious. And we would set that up the same way. Moles of NaCl plus 0.79 moles of H2O, which would equal moles of H2O. Because they're proportional to each other, we can rework this whole problem, and then we can figure out that we can combine this and eliminate things to end up with 0.79 moles of NaCl is set equal to 0.21 moles of H2O. So basically what I did is I took this and I substituted it in. So where it says moles of NaCl, well, I put that over here. So we could actually substitute this in. This is what it simplifies out to right here. So the easy way to put that is the molar fraction of the solvent times the number of moles of solute is equal to the molar fraction of solute times the moles of solvent. And that's what we're going to use. So we're going to use our 0.79 times our moles of NaCl, set it equal to our 0.21 times our moles of H2O, which we have our moles of H2O. So when we set this up, you get 0.21 times our 5.56, divided it by our 0.79, and we get a total of 1.48 moles of NaCl. But the question didn't ask for that. It asked for, hey, how many grams are there? So we know that 1 mole is equal to 58.5 grams of NaCl. And we multiply that out, and you get 86.8 grams of NaCl. Molar fraction is really important for working those equations backwards. So if we know percents, we can use actually the molar fraction because that ratio is set. And it's a nice conversion factor that we can use to get from moles to mass of a substance using very limited information.